Hello, my name is Emily Layton, and today I'll be sharing my research on how the lethality induced by pathogen-blocking bacteria increases with grandmother age. To start, those bacteria are called Wolbachia, which are studied for two main reasons. First, they infect over half of all arthropod species, making them the most abundant endosymbiont on the globe. Second, they block the replication and transmission of important viruses such as Zika and dengue. And for these two reasons, vector control agencies across the globe actually combine Wolbachia's spread and pathogen blocking capabilities to drive Wolbachia into mosquito populations, preventing disease transmission. Wolbachia's exceptional spread is attributable to two things. First, they're vertically transmitted from mother to offspring. Shown in the figure on the right, uninfected mothers produce uninfected offspring, while Wolbachia-infected mothers produce Wolbachia-infected offspring, even if the father is not infected. However, if the father has Wolbachia, while his infected offspring survive normally, his uninfected offspring die. This death of the uninfected offspring is called cytoplasmic incompatibility, or CI for short, and it provides a fitness advantage to Wolbachia-infected females that promotes Wolbachia's spread. To measure CI, we mate an infected male to an uninfected female and calculate the percentage of embryo death. It's important to note that not all of the embryos die, and actually the strength of CI is highly variable. Since vector control programs rely on CI to promote Wolbachia spread in mosquito populations, the strength of CI is critical to Wolbachia's applications. The greater the percentage of embryo death by CI, the faster Wolbachia can spread throughout that population and block disease transmission. So the variation in CI strength is dependent upon the species of the insect host, the strain of Wolbachia infecting the host, the density of Wolbachia, and a number of other factors. However, even when we controlled all of the factors known and published, there is still a high degree of variation in CI strength, represented here on the y-axis as the percentage of embryo death. Each data point represents a different batch of embryos, and in replicate 1, you can see that CI strength varies from under 20%, which is very low CI, all the way up to 100% or complete CI. However, with just one more factor controlled, we were able to reduce the variation and increase that median strength of CI to 100%. This additional age factor is the age of the paternal grandmother prior to producing her sons who induce CI in their own offspring. So to validate our hypothesis that grandmother age affects CI strength, I controlled grandmother age from 2 days all the way to 18 days, as represented on the x-axis. The y-axis again shows the percentage of embryo death due to CI. As you can see, as the grandmothers aged, the median strength of CI induced by her sons increased as well, and the variation in CI strength again decreased. So now that we had seen this effect, we wanted to know why it occurred. Since Wolbachia densities highly correlate with CI strength, as I mentioned earlier, we decided to measure Wolbachia densities in the grandmothers and her sons. To do this, I dissected the gonads of the flies, since Wolbachia are localized in the reproductive tissue. Then I extracted the DNA and I analyzed Wolbachia densities using qPCR. First, I measured Wolbachia densities in the grandmothers prior to mating. Here, the x-axis shows the age of the grandmother, while the y-axis shows the density of Wolbachia. I found that older grandmothers have significantly more Wolbachia than younger grandmothers prior to mating. However, after mating, the Wolbachia titers of both age groups are significantly diminished. The older grandmothers still have higher titers than younger grandmothers. This caused us to wonder what happened to that Wolbachia during mating. But as you remember, Wolbachia are vertically transmitted from mothers to offspring. So we hypothesized that this difference in Wolbachia titers was transmitted to the next generation. So we measured the next generation as embryos, and we found that embryo offspring of older grandmothers have significantly higher Wolbachia titers than offspring of younger grandmothers. Next, we measured Wolbachia titers as those offsprings aged into adulthood. And in males, Wolbachia titers diminish with age, but we still found a trend of increased Wolbachia titers in sons of older grandmothers as compared to younger grandmothers. And this allowed them to induce stronger CI in their own offspring, as we previously saw. So to summarize, we found that Wolbachia accumulate in a grandmother as she ages, allowing her to pass on an increased load of Wolbachia to her sons, who then induce stronger CI in their own offspring. This gives us a new understanding of Wolbachia density dynamics, which actually haven't been studied before in Drosophila females. It additionally increases the utility of the Drosophila melanogaster system, which previously hasn't been used much because of the high degree of variation in CI strength. And lastly, and possibly most excitingly, this is a novel transgenerational influence of the symbiont on its host. So this means that in this system and in many systems, the past matters in affecting present phenotypes. So with that, I'm happy to take any questions. Thank you.